This is the presentation of our research results for the scheme cooperation with university in Malaysia. The title of our research is Multiband Electromagnetic Metasurfaces for Energy Harvesting. Our team are myself, Mudrik Alaydrus, Umay Saroh, and Galang Hakim, and the team from Unimap consisted of Muzamil Yusuf and Hasliza Rahim. Let me show first the background of the research, the development of the increasing development of wireless communications and sensor systems nowadays. We can see there are almost in many places we use wireless communication, and also in order to support the connectivity of sensor systems, we connect them with wireless systems. The problem of such wireless system is we have insufficient energy in the battery, and instead of charging the devices through the normal conventional electrical cable, we would like to use the wireless power transfer technology, WPT, or we could also use the second alternative. We can charge our battery by means of energy harvesting. The aim of this study, the aim of this research is to design a periodic metasurface structure based on small unit cell dimensions, which is we propose a simple structure, and then we will see how the structure can function in several bands. We call it as multiband, and how we can absorb the energy in different frequencies in order to exploit the fileable ambient wireless signals. We conducted several literature study. The first one is that we see in the past that periodic structure connected with full bridge rectifier circuit was developed to harvest the wireless energy, and then a structure consists of based on metasurface with a cross dipole array, which is able to achieve 74% efficiency at the frequency 3 gigahertz with incoming input power of around 16 dBm. And in this case, we use two dielectric substrates. And then another method developed to integrate the SMD diodes into the circuit, and the structure can capture RF energy in dual band 2.4 and 5.8 gigahertz. And we see also a report combining RF electric energy harvesting and solar energy harvesting. And in the case for the RF energy harvesting, the metasurface structure has a bandwidth of 43.6%. And we also study literature showing a conventional absorber, which is able to minimize the reflection coefficient, and in this case with a conventional dielectric layer. And the metamaterial absorber at the time show only a very small available power density, and then some researcher proposed a supercell structure which is able to convert the electromagnetic energy to AC energy with a conversion efficiency of 70% at the frequency of 2.4 gigahertz. And with additional layers, we can build a multi-layer structure. Uh, in this case, is able to work at 3 different frequencies with absorption efficiencies of 90%, HD3%, and HD1%. So, in this research, we propose a very simple structure consisting of two FR4 layers separated by a gap. As you can see here, the structure is a so-called multiple split ring resonator, and we use in this initial design 2 chip resistors which present the load for consuming the absorbed energy. So we set here the geometry W1, W2, W3, and the position here for the chip, and also the width of the middle line, the length of the dimension here, and then we did the parameter study. In this case, for example, we did the variation in the Lx from a small one, 25 millimeter to 34. In this case, we have the structure without chip resistor and also without the middle line. As you can see here that the reflection factor is very big. And if we add the middle line, we can improve the reflection factor. However, we need the chip resistor. And now for the next result here, as you can see, this is a very nice result. We integrated chip resistor on both sides, and we make variation for the value of the chip resistor. For the case of here, the red curve, R equals 0 ohm, it means we connect the structure with a metallic line. And as you can see here, if we make a variation for the value of the chip resistors to 500 ohm, we got the blue lines. And if we have here for the 1000, the black line, and again here for higher chip resistor. And as you can see here, for R equal 1000 ohm, we get the very small reflection factor. And if we calculate with the following equation, we get the absorption in percentage here. As you can see, for the frequency around 1 gigahertz and here 2.15 gigahertz, we have absorption of more than 90%. So, and now in order to give the opportunity, the structure for working at the different frequencies, the multiband characteristics, we built here additional structure in this position, and this is again the geometry. Although we got here resonances, however the value is still small. So what will we do? We did a small variation modification here, and in this second design, we have more resonant phenomena. However, they are small. They are still small, less than 70%. So, and for the third design, we make here a gap, a breaking, and as you can see here, for the resistance of 1000 ohm, we get now a very good result here at the following frequencies. Here around in the vicinity of the JSM signals, so we can use this wasting signal around us. And here also for the other frequencies, maybe we can change it with if we do here small variation in the structure. So, and then we have also tried to observe the design 4 and design 5. However, we got no significant improvement. So we propose now the design 3, in this case, the following, and we have here as the best design with the following settings of the geometry, and we have in this case around 4 different frequencies, also quad band, and we have the following absorption rate. This is a little bit small, but however it is still 87% of the signals is absorbed. So, and now we come to conclusion. We have designed multiband metasurface structures using multi-resonator structures. So in this case, we see that we can get a multiband characteristic of the metasurface, and as you see, computer simulation shows that we can achieve more than 90% absorption level at 4 different frequencies. So, and now this result and this research and the consequences results, we can attach to the following lectures. In the bachelor program in electrical engineering, we can show these results in the lecture electromagnetic fields or in the lecture IoT. And in the master program of electrical engineering, we can attach this research and results to the lecture RF and microsystem. So thank you very much for your attention.